Did you know that if you shrank the entire observable universe down to the size of Earth, our entire Milky Way galaxy would be smaller than a single atom? Not a grain of sand, not a speck of dust, an atom. And if that didn't just make your brain stutter for a second, hold on, because we haven't even started yet. We haven't talked about what lives below the atom. We haven't talked about the things so small that even atoms look like entire solar systems compared to them. And we haven't talked about what sits at the other end, the structures so incomprehensibly vast that the entire history of human civilization, every war, every empire, every love story, every invention, is less than a rounding error in their timeline. By the end of this, your sense of scale will be permanently broken. And I mean that as the highest possible compliment. Let's begin where you are right now. You, a human being, somewhere between 1.5 and 2 meters tall. That is your anchor point. That is the only unit of measurement your brain was actually built to understand. Evolution gave you a mind calibrated for this scale, for hunting animals, for building shelters, for reading the expressions on other human faces from across a campfire. Your brain is extraordinarily good at understanding things within a few orders of magnitude of your own size. A mouse, a tree, a mountain, a continent. These things stretch your intuition but don't break it. What we're about to do is go so far in both directions from where you stand that your intuition will simply stop working. And that is not a failure. That is the beginning of wisdom. Let's go small first. Pull back just slightly from the human scale. A human hair is about 70 micrometers wide. That's 70 millionths of a meter. You can't see a single micrometer with your naked eye, but your brain can still kind of picture it. A hair. Thin. Fine. Now go 10 times smaller than that. You're at the scale of a red blood cell, about 8 micrometers across. Still biological, still something that exists inside you right now, billions of them coursing through your veins. But your ability to picture this is already getting fuzzy. Go 10 times smaller again. 1 micrometer. You're now at the scale of a large bacterium. A living thing. A creature with a membrane and internal chemistry and the ability to reproduce. 1 micrometer. A millionth of a meter. Invisible to you without a microscope. But still, in the grand scale of things, enormous. Now go 100 times smaller than that. You're at 10 nanometers, 10 billionths of a meter. You are now at the scale of a large protein molecule. The machinery of life. The things that actually do the work inside your cells. The enzymes that copy your DNA. The motors that carry cargo along microscopic highways inside your neurons right now as you watch this. These protein machines are 10 nanometers across, and they are folded into shapes of staggering complexity that took billions of years of evolution to perfect. And you cannot see them. You cannot image them with visible light because they are smaller than the wavelength of visible light itself. Light physically cannot resolve them. We use electron microscopes and X-ray crystallography to understand their shape, and even then, understanding how they work took decades of the brightest human minds working at the absolute edge of our capability. Go 10 times smaller. 1 nanometer. You're at the scale of a DNA double helix. That twisted ladder you've seen in pictures, its width is about 2 nanometers. The distance between each rung is about 0.34 nanometers. In every single cell in your body, there are about 2 meters of DNA packed into a nucleus that's only about 6 micrometers across. The packing ratio is insane. If you scaled up a cell nucleus to the size of a basketball, the DNA inside it would stretch for about 40 kilometers. And that DNA contains the instructions, the code, for building and operating you. Written in a molecular language using 4 chemical letters, copied billions of times across every cell in your body with an error rate of less than 1 mistake per billion base pairs. The universe built a self-replicating information storage system at the nanometer scale that outperforms anything human engineers have ever built. And it fits inside something you cannot see without a microscope. Now we arrive at the atom, about 0.1 nanometers across, or 1 angstrom. This is where things start to become genuinely philosophically disturbing. Because when you picture an atom, you probably picture something like a tiny solar system, a nucleus in the middle with electrons orbiting around it. And that image, while useful, is deeply misleading. Because if you scaled an atom up so that its nucleus was the size of a marble, about 1 centimeter, the electrons wouldn't be orbiting a few inches away. They'd be somewhere between 500 meters and a kilometer away, with nothing in between. An atom is almost entirely empty space. And not just a little empty, overwhelmingly, almost perfectly empty. The nucleus, which contains essentially all of the atom's mass, occupies an almost incomprehensibly tiny fraction of the atom's volume. If you removed all the empty space from every atom in every human body on Earth, all 8 billion of us would compress into a volume smaller than a sugar cube. The density of matter we experience as solid and real and physical is almost entirely the story of forces, electromagnetic forces between electron clouds, rather than actual substance. You are not solid. Nothing is solid. Solid is a feeling your electrons give your brain. Reality at this scale is almost nothing. But we're not done going small. We're not even close. Go inside the nucleus. You're now at the scale of protons and neutrons, about 1 femtometer, or 1 quadrillionth of a meter. A proton is about 100,000 times smaller than an atom. And inside the proton, inside this thing that physicists once thought was fundamental and indivisible, there are quarks. 3 of them, held together by particles called gluons through the strong nuclear force. The strong force is the most powerful fundamental force in the universe. It is approximately 100 times stronger than electromagnetism, 1,000,000 times stronger than the weak nuclear force, and 10 to the power of 38 times stronger than gravity. It is what keeps the nucleus of every atom in your body from exploding. The reason matter exists, the reason you exist, is because this force is strong enough to overcome the electromagnetic repulsion between positively charged protons packed into a tiny nucleus. Without it, every atom would fly apart in an instant, and there would be no chemistry, no stars, no planets, no life. This force, operating at the femtometer scale, is the reason anything exists at all. And below quarks? We don't know. We genuinely don't know. Our instruments can't probe smaller than about 10 to the minus 18 meters, the attometer scale. At the Planck length, 10 to the minus 35 meters, the very concept of space as a continuous smooth fabric may break down. Quantum mechanics predicts that at this scale, spacetime itself might be foamy and discrete, not a smooth sheet but a bubbling, fluctuating quantum foam where the notion of distance and location stops meaning what you think it means. We have never probed this scale. We may never be able to. It may require energies so extreme they are physically impossible to achieve with any conceivable technology. The bottom of reality might be permanently hidden from us. Let that sit for 1 second. We genuinely do not know what the universe is made of at its most fundamental level. We have extraordinarily successful theories that describe particles and forces, but whether those particles are truly fundamental or are themselves made of something else, strings vibrating in higher dimensions, perhaps, as string theory suggests, we don't know. The floor of reality might be a mystery forever. Now, let's come back up. All the way back up through the atom, through the cell, through the human body, and let's go the other way. Let's go big. At the scale of the human body, you are standing on a planet. Earth, 12,742 kilometers in diameter. Almost 13,000 kilometers. If you started driving right now at highway speed, and you could somehow drive straight through the Earth, ignoring the molten core, ignoring everything, just driving, it would take you about 6 days of continuous driving to come out the other side. The distance from the surface to the center of Earth is so large that if you stacked every human who has ever lived end to end, you still couldn't reach it. Earth is enormous by the standards of anything your ancestors ever encountered. And yet, the Sunday 1.39 million kilometers in diameter. You could fit 1.3 million Earths inside the Sun. 1,300,000. If Earth were the size of a marble, the Sun would be about 1.5 meters wide, taller than many people. The distance from the Earth to the Sun is about 150 million kilometers. Light travels at 300,000 kilometers per second, the absolute speed limit of the universe, and it still takes that light about 8 minutes and 20 seconds to reach you from the Sun. When you look at the Sun, and please don't, you are seeing it as it was 8 minutes ago. You are looking into the past. The Sun you're seeing right now might have already changed in some way, and you won't know for another 8 minutes. That's how far away it is. Now step back further, way further, to the edge of our solar system. The Voyager 1 spacecraft was launched in 1977. It has been traveling continuously for nearly 50 years. It is now about 24 billion kilometers from Earth. It is the most distant human-made object in existence. And at that scale, the nearest star, Proxima Centauri, is still more than 160 times farther away than Voyager 1. If Voyager were heading for Proxima Centauri, which it isn't, at its current speed it would take about 73,000 years to get there. 73,000 years. Agriculture was invented about 12,000 years ago. We'd need to invent it 6 more times and wait that long again before Voyager arrived. Interstellar distances are not merely large. They are of a different category of large than anything human experience prepares you for. The nearest star is 4.24 light-years away. Light-years. The distance light travels in an entire year. 1 light-year is about 9.46 trillion kilometers. Proxima Centauri is 4.24 of those, and it is our closest stellar neighbor. Alone on our block, and our block, the Milky Way galaxy, contains somewhere between 100 billion and 400 billion stars. Let's say 200 billion. If every star in the Milky Way were a grain of sand, you'd have enough sand to fill multiple Olympic swimming pools. And the Milky Way is about 100,000 light-years across. If you tried to drive across the Milky Way at highway speed, it would take you approximately 1 with 15 zeros after it years. The number doesn't even have a common name. But the Milky Way is just one galaxy. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.537 million light-years away. And it is coming toward us. At about 110 kilometers per second, it is on a collision course with the Milky Way and will collide in approximately 4.5 billion years. A collision between two galaxies doesn't mean stars smashing into each other. Space is too empty for that. It means the gravitational structures intertwining over billions of years, the galaxies distorting and merging, and eventually becoming one enormous elliptical galaxy. Our sun will probably be flung into a different orbit. Earth may survive. Humanity, if it still exists in any form, will watch the sky transform over millions of years as two galaxies become one. Now go further. Much further. The observable universe contains an estimated 2 trillion galaxies. 2 trillion. And each of those galaxies contains, on average, hundreds of billions of stars. The total number of stars in the observable universe is approximately 10 to the power of 24. 1 septillion. That is a 1 followed by 24 zeros. For context, if you tried to count to 1 septillion, counting one number per second without stopping, it would take you longer than the current age of the universe. By an enormous margin. And those galaxies are not scattered randomly. They form structures. Groups of galaxies, then clusters of hundreds of galaxies, then superclusters, the largest structures in the universe. Our galaxy belongs to the Virgo supercluster, which contains over 1,300 galaxies and spans about 110 million light-years. And even that is just one small part of a larger structure called the Laniakea supercluster, our cosmic home, which spans 520 million light-years and contains the mass of 100 million billion suns. And beyond superclusters, there are filaments, enormous thread-like structures of galaxies stretched across the universe like the strands of some vast cosmic web, separated by equally vast voids, empty regions hundreds of millions of light-years across where almost nothing exists. The cosmic web, the largest structure in the observable universe. Threads and sheets of galaxies surrounding enormous bubbles of near emptiness. When you look at a map of the large-scale structure of the universe, it looks strikingly like a neuron, like a nerve cell, like the same branching, connected, web-like structure that exists inside your brain. The universe at its largest scale looks like the structure of the thing we use to think about it. No one knows if that means anything. It might be coincidence. It might be something more. We don't know. The observable universe, the sphere of space from which light has had time to reach us in the 13.8 billion years since the Big Bang, is about 93 billion light-years in diameter. Not 13.8 billion, because the universe has been expanding the whole time, stretching the space between galaxies, so that the most distant light we can receive came from regions of space that are now much farther away than they were when the light left. And beyond the observable universe, beyond the cosmic horizon, there is almost certainly more universe. Possibly infinite more. We cannot see it. We cannot receive any signal from it. It is as inaccessible to us as the inside of a black hole. But our best cosmological models suggest it exists, possibly going on forever, possibly containing not just more of the same but regions where the physical constants themselves are different. Different strengths of gravity, different masses for particles, different outcomes in the lottery of cosmic structure formation. Some of those regions might be places where stars cannot form. Some might be places where chemistry is impossible. Some might be places where nothing interesting ever happens. And some, statistically, if the universe is truly infinite, might be places almost identical to ours, where something is watching a video very much like this one. Now come back. Come all the way back. Back through the filaments and the superclusters and the galaxies and the solar system and the planet and the room and the screen in front of you. Back to you. You are a collection of atoms forged in the cores of dead stars. The iron in your blood was made in a supernova, a stellar explosion so violent it briefly outshines an entire galaxy. The carbon in your DNA was cooked in the belly of a red giant. The calcium in your bones was scattered across space by stellar winds over billions of years before gravity gathered it into the cloud that became our solar system. You are not separate from the cosmos. You are a local expression of it. The universe built stars to make heavy elements. It built planets to give those elements a place to combine. It built life to give those combinations a way to persist and replicate. And it built minds to give all of it a way to look back on itself and ask, what am I? How big is this? What does it mean? There is no other known place in the universe where that question is being asked. No other confirmed location where matter has organized itself into something capable of measuring its own context. You are the universe's way of being astonished at itself. From quarks to the cosmic horizon, across 60 orders of magnitude of scale, through structures of incomprehensible size and structures of incomprehensible smallness, the most remarkable thing we've found is not any individual object. It's that anything exists at all, that the numbers worked out, that the forces balanced, that the constants landed in the narrow range that permits complexity, that you are here, in this exact moment, capable of being amazed. Don't waste that. Don't waste a single day forgetting how extraordinary this is. If this video cracks something open in you, share it with someone who needs a reminder of how vast and strange and beautiful this all is. Subscribe, because we make this kind of journey every week. And now I want to know, what scale genuinely breaks your brain the most? Is it the Planck length at the bottom of everything? Is it the 2 trillion galaxies? Is it the fact that atoms are almost entirely empty space? Tell me in the comments. I want to read every single answer.